Okay, this video is about infinite limits. So these are limits where you see x is going towards infinity or x is going towards negative infinity, as it turns out. All right, so the basic idea, as stated there, is we want to look at what happens when x gets arbitrarily big, or if you're talking about negative values of x, absolute value of x gets arbitrarily big. First, we're going to look at this from a few graphs on it and sort of see how it can change from place to place. So first, let's look at number 1. There you see if x is a really big number, it seems like the function is decreasing, and that seems to be going forever. So that seems to be approaching some arbitrarily small value, so that as it's going there. In the other direction, though, it seems to be doing something different. I put in the dashed line at L for a reason. So what you see there is that the function seems to want to get closer and closer to the value L, but it doesn't actually ever touch it. So you may be familiar that this is a horizontal asymptote. So that's kind of, you can see there's now a connection between infinite limits and what a horizontal asymptote is. So moving over here to number 2. So when x is big, now the function seems to be growing rather than decreasing. But on the other side, the function is also decreasing when x is a very small negative number and continues to go that way. It seems it wants to get arbitrarily small itself, not just x, but the function value. That doesn't have to happen. We could have kind of the opposite situation in number 3 right here, and that no matter which side you pick, it's going to go to a different value, but it does seem to approach a particular value. So, for example, I'll be a little bit more explicit. When x goes to infinity, then the function value seems to want to go to m. And similarly, if x goes to negative infinity, the function value wants to go to n. And remember, x can't ever equal infinity, right? X is not equal to infinity because we can't ever say that nothing ever reaches infinity, so you can't say anything is equal to it. Of course, in some cases, we don't get anything like that. Here at number 4, what happens is that it doesn't seem to be approaching a particular number. The function kind of looks like sine x. So it's oscillating back and forth, and so it doesn't seem to approach anything. So the limit doesn't go to anything. Here, the function doesn't approach anything. Okay. Doesn't approach a number. But a warning, a big warning for this, if that doesn't happen, if we're saying that the limit is equal to infinity, which seems like it doesn't make a lot of sense because we're saying like, well, you can't say x is equal to infinity and you can't substitute x equal infinity. That's not allowed. But we can say that the limit is infinity. That's sort of a catchphrase. What this means actually, as you see in blue here, it means that the function grows without bounds, or it gets arbitrarily large. So if you're talking about this approaching negative infinity, you're saying the absolute value of the function is growing arbitrarily large. With that in mind, the approach is whenever you have an infinite limit, basically that's when you have x approaching infinity or x approaching negative infinity. Pretty much like all other limits that you have, this can go can approach a number, can approach infinity or negative infinity, i.e. grows without bound, or as we saw in that last example, does not exist. So in that case, It doesn't approach. Now, the last two are both not approaching anything technically, but remember that it just is saying they have very different meanings. So you've got to be really careful about what the difference is between those two, okay? And finally, the way to look at it, I want to do one really quick example. There's several different ways of approaching limits, as it turns out. But I think seeing one particular example might be helpful to you, and you can see other ones in your classes. So in this particular case, we're saying limit as x goes to infinity. Let's say it's 5x cubed minus 4x plus 6 all over x to the fourth plus, let's call that x cubed instead of x to the fourth. As it turns out, it's more fun that way. 2x squared minus 11. All right. Now, I'm going to do this sort of the official way and then tell you another sort of approach to it. Actually, two other approaches to it. So method one is you look for the highest one. So note, just so that we know, is x is much bigger than a number, right? If x is going to infinity, any number that you can think of in your head, like 6, 11, 1 million, x is going to be much bigger. But x squared is much bigger than x. Well, think of it this way. Basically, it's infinity, and I'm putting it in quotes because you can't ever really do this, times infinity. So you can say like, well, x is going to infinity, but x squared is infinitely bigger than x. It's infinity times infinity in some sense. And you can keep on going that x cubed is much bigger than x squared, etc. And you could keep going that on and on. The reason it's valid here is because if we look at what we're talking about in this particular problem, you notice that the highest power of x are cubes. So those are going to be the biggest value of the function. So we want to deal with this in a way that's much more systematic. So what I'm going to do here is get rid of everything that doesn't involve x. I'm going to try to multiply it through and make it easier to see. So the highest power of x cubed, let's get rid of the x cubed. So multiply by 1 over x cubed. We do it in the numerator, we have to do the same thing in the denominator. You always look for the highest power of it. So going back down here, remember you have to keep your limit symbol every single time. Multiply through, being very careful about the powers. As you can see there. And what happens is that the highest power conveniently is just a number now. Well, why should I care about that? The idea behind this now is that everything else, we have a number over something that's huge. So large denominator means that we're going to have a tiny fraction. So in this case, the denominators are getting bigger and bigger and bigger without bound. That means the fractions are getting smaller, smaller, and smaller without bounds again. As such, what we want to do then is to note, like, well, the number 5 is going to stay that way, but 4 over x squared, that's going to 0. 6 over x cubed, that's going to 0. Then 1 plus 0 minus 0 is 5. And that is going to be our limit. So there are other methods and other ways of doing this. But I'm going to leave that for something that you talk about in class and it'll work out really well. You can